Okay, so in this video, we're going to talk a little bit about how to implement this try structure. We're going to take a first pass at implementing it, and in the next video, we'll talk about some extra implementation details for what you'd see in maybe a more advanced implementation. So before we talk about how to implement this, we need to mention one thing about how computers represent characters. So computers only know how to understand numbers. In fact, they don't understand the numbers that we know, like our favorites, like 1, 10, or I don't know, any number that might be your favorite. They only understand numbers that are ones and zeros in binary. And so anything that you want to represent to the computer, you need to represent as a number in binary. Now, the nice thing is that there is a really convenient mathematical formula if I'm converting numbers that we know, decimal numbers, numbers in base 10, to this binary system of numbers in base 2. So in some sense, we don't need to think about everything in being in terms of binary. We need to think about things in terms of just numbers in general. And so when it comes to representing things like strings, we need to represent each character in the string as a number. And in some sense, how you choose which number is associated with which letter is somewhat arbitrary, as long as it's standard, so that everyone can agree on what the number 7 means in terms of characters. So some old encoding that came around, I don't remember when this came around, called ASCII, which stands for the American Standard Code for Information Interchange. I don't know why I have brain cells dedicated to that, but it's just a table that says the letter A is represented by the number 97. B is 98, C is 99, etc. And you could already imagine a whole set of problems with this implementation, namely the A, American, they really take America to heart in this, meaning that we don't really have character encodings for non-American English characters. So we don't necessarily have encodings for Spanish, where you have accents or tildes over characters. Nonetheless, Japanese or Mandarin, where you have a whole different encoding, like written language than our character-based language that we use in American English. So ASCII is an old system. It is not what's currently used. They use this kind of fancier thing called Unicode, which is able to work for basically a universal encoding language for all possible languages, but it's more complex. So we like to think about ASCII because it's simple, even though it's not what you actually see, but the big idea is the same. It's a table that tells you for any particular letter or symbol that you care about, here is what the number is. So in ASCII, there are 128 possible characters. All the lowercase letters, all the uppercase letters, a lot of the punctuation we use and numbers. There's 128 possible. So the reason I bring this up, this number 128 shows up quite a lot in the remaining video here, which is if we want to kind of think about how to represent this try is going to have children, one for each possible character or each character that does exist in the dictionary. So instead of having a binary tree, we're going to have a 128-ary tree, where each node has at most 128 children, one for every next possible character. So when we're thinking about how to represent this in code, we're probably going to have, in our try, have some kind of node to represent each node. And that node is going to represent what character is there, whether or not that node corresponds to a word, so if it's a key. And it's going to need some kind of map structure that says for any particular character, what's the next node? But when you're currently at this node for this A here, if you want to get the node corresponding to a D from here, then you can say next.get D, and it returns this node. So we're going to have some kind of abstract map here. That's why I call it a data index care map, as some abstract term of some kind of mapping from characters to the data we're interested in. And so if we want to represent this kind of try with 128 possible children, one kind of natural way of trying to do that is, well, if all of the characters are numbers between 0 and 127, then we could just represent these things as a big old array, right? So for each node, it's going to store internally inside this map kind of a really, really big array with 128 possible slots. And those slots store references to future nodes down the tree. So for example, I show you the zoomed in picture of each of these nodes. So in this abstract picture of the tree that represents the word up, the U is going to have the character U. Its is key is false because U is not a word in the dictionary, just the letter U. And its next field, this kind of data index char map, is going to have just a big array that stores for the letter P, which has ASCII code 112, a reference to the next node. And that node will be P, and it will have all of its own fields and its own array map. So that's the kind of big idea. So just use a big array to store all of these things. And now when you have a trie that's arbitrarily large, each one of these nodes has kind of a big array to let you access any of its 128 possible children. Now, you might already start to see that this representation is a little inefficient, right? Because there are lots and lots and lots of characters in our language. And if we have kind of this trie representation with a node per character, that's a lot of arrays of this 128 size. So this seems really space inefficient. And we'll find that this actually is going to be an inefficient implementation. So what we're going to start working on in the rest of this video and the next videos, or the next video, is kind of steps we can take to try to improve this. But in an abstract sense, that's it to implementing a trie. You have a node class, and to get this sense of having any possibility of getting to the next node, any possible character, we need to, instead of having a left and right child, we have some kind of map that says for any particular character, what's the next node. And here we're using the ASCII representation to give us an array of a certain size, so we can just index into that array. So the first thing I'm kind of curious and trying to figure out is, can we remove some of our memory redundancy here? So some kind of unnecessary memory that's used. And so if you look at this picture of this like larger trie, and each one of these nodes has lots and lots of array slots in them, and most of these are going to be null. So you can see here that I'm showing like little crosses through some of these in the sense that they don't have children from them, or that child is null. And so a lot of these arrays have lots of nulls. So the question is there anything in this structure that can help me remove some information that's encoded unnecessarily? And one kind of tricky and subtle realization is that the letters themselves are being stored twice. So consider this character A here, that's saying that this node represents A. There are actually two ways we know it's represented by an A. The first being we're storing a field here that says this is A, but we also know that this node must be A because we got there from the A branch. When you start at the empty string and then go down the A branch, this node needs to represent A. So kind of the first optimization we'll make is noticing that the branches themselves tell us about the characters. There's no need to also store the character in the node itself. So what we'll do is we will just go through and delete all of the character fields from the nodes themselves. The way we'll find characters from now on is actually going through and using the keys from that next map, saying like, oh, this is the node that I get to from A. Well, I'll pass that information along whenever I'm working with it. So to give you a chance to try and think about this, let's think about a trie and how you build one up. You add words into it. My question is, does the structure of a trie depend on the order of insertion? So if I insert data followed by aqua versus aqua and then data, does the order of insertion into a trie affect the final structure of a trie? Take a second and try to reason about that on your own. Yes, no, or you're not quite sure yet. Okay, now you had some time to think about that. I would argue that the order of insertion does not matter here, that this does not have an effect on the structure of the trie. The reason being that if you use my example I just used of aqua and data, adding aqua first is just going to build up that path for aqua, and then adding data builds up the path for data. But that shouldn't matter if you add data first and then aqua. Even if you add two words that share a prefix, like data and dad, data builds up the data path, and then dad starts with the path that's already there, DA, and then goes down to D afterwards. So you'll still end up with the same trie no matter how you build it up. So that's kind of like just thinking about how these things work. What I have at top, I'll just hide my webcam real quick, is just a picture of this trie with like the many possible references. Remember, I mentioned that if you're using an array implementation, you're going to have 128 slots. And even if you have just one child, that means the others will be null. So before we talk about some fancier implementations of this trie, I want to talk about this array trie. Besides being a little bit memory inefficient, is actually kind of as good as it gets in terms of runtime. So if we think about the runtime of our operations we care about on a set of strings, if we had n strings and we're treating the length of those strings L as some constant, so we're not going to assume it's much less than L. So it'll basically be constant time. If we consider our balanced binary search tree of all of these words, we saw that log n performance. And the hash map, we saw the O of 1 in practice, but technically O of n worst case. Now, if we think about our trie, then we actually get this O of 1 runtime. Now, technically, it's O of L, the length of the strings, right? Because you have to go down the height of the tree, which is the length of the longest word. But we're assuming here that L is a constant with respect to the number of words in the dictionary. So I highlighted these to show you that it's actually a really good implementation of our set of strings. But it also is much better when it comes to that keys with prefix operation. Finding all the keys that start with a particular prefix, both our balanced binary search tree and our hash map would have to scan over all of the keys because they're not organized for prefixes. And our keys with prefix on our trie would be something like a theta of p operation, where p is the number of words that start with that prefix. Now, the reason is you're still going to have to iterate over all of the words that kind of belong in that section of the tree. But in some sense, that's like a lower bound on what you need, right? Like if your prefix, if there are 100 words that start with the prefix DA, then of course your runtime is going to have to be at least 100 steps, right? Because you have to go gather all of those words. So at a minimum, you're going to have to just go over all the results. But the nice part is that you don't have to go over anything extra. And so I kind of have a note here. P is kind of a made up quantity, right? It's just the size of the result. But normally P is much shorter or much smaller than N itself. So that usually should give you a really big speed. So we can kind of already see here that some big takeaways about this implementation is that when the keys are strings, tries give us a better add and contains runtime, meaning that they work better as sets than necessarily a binary search tree or a hash map. The big downside so far is that they take up a lot of memory, because in order to do this, we kind of need a lot of arrays that are really large in each node. And so in our next video, let's talk about some optimizations to try to reduce the amount of memory necessary in order to represent these structures.